Hi, everyone. Welcome back to the new quantum era. I'm Sebastian Hassinger. Today, I'm talking with Matthijs Rijlaarsdam, Matt, co-founder and CEO of QuantWare, the Dutch company that has quietly become one of the world's largest commercial suppliers of superconducting quantum processors. Here's the thing that grabbed me about this conversation. The quantum computing industry has been stuck at roughly 100 qubits for the better part of a decade. Google went from 53 to 105 qubits in 6 years. IBM's next big target is 120 qubits in 2028. And the reason isn't physics, it's primarily wiring. Something like 90% of the chip area on a current superconducting QPU is consumed by signal routing, not by qubits. It's an engineering bottleneck, not a fundamental one, and QuantWare claims to have solved it. Their architecture is called VIO, Vertical Integration and Optimization, and it's a 3D chiplet approach that routes signals vertically through a stacked silicon cube instead of along the chip edges. The headline number is 10,000 qubits by 2028, which would be 100 times larger than anything in the industry today. And their roadmap goes to 1,000,000 qubits by 2029 using arrays of these modules. Now, if you've been listening to this show for a while, you'll know that I'm going to push on claims like that. And we do get into the gap between announcements and demonstrated performance, what the analysis that ran in post-quantum called turning the marketing volume up, and why 10,000 physical qubits is still a long way from being a production-relevant quantum computer. But what makes this conversation really interesting to me is the business model argument, frankly. Matt makes a forceful case that the quantum industry needs to start behaving like the semiconductor industry, that vertical integration is a dead end, and that specialization and volume economics are the only realistic path to useful quantum computing. He draws a direct analogy to TSMC. QuantWare doesn't build quantum computers, they sell the processors that go inside them. And I think whether you agree with that bet or not, it's one of the most important strategic questions in the industry right now. We also get into some great stuff about the Dutch quantum ecosystem, how consistent government investment through Quantum Delta over a decade plus has created this remarkable cluster of startups out of TU Delft and QuTech, and why Matt thinks quantum computing will ultimately be heterogeneous, with superconducting processors playing the role of fast compute, while trapped ions and neutral atoms handle memory-like workloads. It's a nice framework. Matt's also just a great talker. He's a computer scientist, not a physicist, which he and I will bond over. And he founded QuantWare at about 25 years old after doing strategy consulting at a nonprofit. It's an unusual path to running a quantum hardware company, and it shows in the way that he thinks about the problem. This episode is brought to you by Qubits OK, a dedicated job board and research digest for quantum computing. If you're building a career in quantum or hiring for one, this is the signal in the noise. Every week, they send out curated job alerts filtered by over 400 specialized quantum tags, trapped ions, QEC, quantum ML, all of it. And they run a daily archive digest that surfaces the papers that actually matter to your specific research interests. This is actually how I found Qubits OK. Initially, I've been trying all the various ways to make sense of the enormous volume on QuantPH. And Qubits OK really does that for me, and I go there on a daily basis, and that's what makes them really powerful as a job listing site. It's free to subscribe. Head to qubitsok.com and sign up in 30 seconds. And if you're hiring in quantum, use the code NEWQuantumEra-50 for 50% off your first job posting. That's qubitsok.com, code NEWQuantumEra-50. The link is in the notes. Hi, Matthijs. Great to see you. Thank you for joining. I've been looking forward to having you on the podcast for a while. Can you start by, you've had a really interesting journey. You're now co-founder and CEO of a very successful quantum computing company, QuantWare. How did you get to that point? I think that's always fascinating to hear.
Well, first off, thanks for having me. Great to be here. Always wanted to be here, of course. So I'm actually a computer scientist by background, um, and I did at some point during my thesis research, I did research at QuTech, which is a large, arguably one of the best, but definitely one of the largest quantum computing research institutes here on the TU Delft campus. Um, on the simulation of quantum computers on classical computers. So I'm not a physicist, so that's always a little, atypical in our space.
Neither am I,
Well,
so I deal with that too.
well, here we are.
Yeah.
And so
Let's talk about the physicists behind their back.
Yeah, exactly. Let's do that. No one is listening. Yeah. So I was doing research on kind of trying to look at the question, what can a quantum computer calculates that a classical computer can't calculate, right? Like that's I guess, one of the most interesting.
That's the $1 trillion question.
Yeah, right. Like, I mean, if you think about it, it's equivalent to the, universal theory of everything in physics, right? Like if you can answer that exactly, you'll probably win like, 10 Nobel Prizes or something. Anyway, so the idea is, if you look at simulating quantum computers on classical computers, if you can simulate a quantum circuit on a classical computer, it's probably not very quantum-y, right? It's probably not so interesting. So anyway, so I was doing that, and then through a mutual friend was introduced to my co-founder, Dr. Alessandro Bruno, our CTO, who at the time was the lead fabrication, the lead quantum chip maker of the DiCarlo lab. And we got to talking, and he kind of had this. At that time, they were working. They were. I think just at the end of the Intel QuTech IARPA collaboration, where they made first some of the most impressive first quantum error correction demonstrations, et cetera, et cetera. And then they were thinking about scaling up, and if you want to scale up superconducting chips, you run into certain problems, right? And still the field hasn't solved those. We're still kind of, Intel announced at that time a 49 qubit chip, and the state of the art is maybe like pushed to 100 or so, right? Like IBM will be in 120 qubits in 2028 still. And so they had this concept that we now call VIO, for vertical IO. We got to talk and we hit it off, and we were able to spin out that team and that concept and some of the IP of the Intel collaboration, and the rest is history. Here we are.
Yeah. I mean, that's really interesting. So you just started, you sort of launched VIO, I guess, towards the end of last year at Q2B. You did a keynote where you talked extensively about it, but it really was the thinking right at the very launch of the company. I guess that's 2020 or 2021, roughly 5 years ago, right? Wow, that's really interesting.
It's right. Like we basically, we worked intentionally in silence on VIO for about 5 years to, we spun out a team which, best GPU architecture team in the world. But the idea was to kind of build up this head start, get this far enough along that we actually have data and can show it, and it's not just a cool render and a concepts. And in parallel, build up this market share, right? Like we launched immediately with the world's first commercially available quantum processor, which was only a 5 qubit chip, right? Soprano, with the idea that the more volume we can get and the more we can change the predominant business model in this industry, that is preparing the market for when we introduce VIO. And so it's an interesting moment indeed. Like as of December, we're talking about it publicly, and really looking forward to the impact we'll make on the world with that. Yeah,
that's really exciting. So you mentioned sort of the the product line of full integrated QPUs or packaged QPUs like Contralto, and that's sort of analogous to like an Intel business model, right? You're selling chips that people can use, and I think mostly they're being used in, like, I know the Israeli Quantum Computing Center has a QuantWare chip and a quantum machines integrated system that they use for research. There's other systems like that in, I think, Korea and Colorado, and others where it's test beds and research devices that are powered by QuantWare. Is that sort of accurate?
Um, I mean, that's definitely part of our business. So today, the majority of our revenue comes from, indeed, as you mentioned, QPUs, QuantWare designed and fabricated and packaged processors. Um, we sell those primarily to commercial entities that typically are indeed developing quantum computers to then sell those computers or the resulting compute. And yeah, some of the examples you mentioned, I think, are good examples of that. Um, and yeah, and as you mentioned, this Intel business model. I mean, when we started, we still even used that in our public marketing, and now, for obvious reasons, we're kind of use different analogies, but I think the analogy still holds, right? Like the exact same economic principles of the classical compute space, where this drive to specialization, increased volumes, which led to near monopolies for Intel, for instance. That is the exact same laws of economics that apply to this space.
Really? So you think that will happen if the modalities converge on superconducting, or even if we have multiple modalities that have viable commercial use cases in parallel with one another?
So I think, I mean, um, everyone will say, of course, my platform is best,
Of
right?
course.
But actually, I think our view is a lot more nuanced. So we think that quantum computing will be heterogeneous in the sense that a lot of these platforms are very sensible, but they have different trade-offs. But you can even see I think this is becoming a more mainstream view. Like, there was this HARC project from DARPA recently announced. This is becoming more mainstream. But you can think of this as, certain platforms, say neutral atoms or trapped ions. They have fantastic fidelities and really long coherence times, but they're very slow operations. And so probably they're quite suitable for more memory type applications. And then you have, well, say superconducting, which is very fast, but as a counter to that, very error prone. You need a lot of error correction. And so that, but it's very fast. And if you want to do quantum compute at scale, the speed of operation really matters, right? Like, there was this kidney paper from last year that with 1,000,000 qubits, superconducting qubits, you can crack an RSA key in about a week. Well, imagine being 1,000 to 1,000,000 times slower than that, right? Like that's for compute, it's not going to be great. And I think the analogy here is, again, go to classical computing, right? Like, you wouldn't want to, process your data on your hard drive, like that'd be super slow. But you wouldn't want to store a Blu-ray video
Right, in your RAM.
on your CPU, yeah, or your RAM today is even worse, yeah.
Yeah, exactly. It's way too expensive. Okay, that makes sense. And you think within those parallel modalities, there's still there's the scaling advantage. When you're a specialist in one of those modalities, you can deliver performance at a scale at economics that others can't match.
Yes, I would even say that more strongly. Like, there is no path towards useful quantum computing without specialization. That is a total fantasy. I'll give an example. We announced, we announced VIO 40K, and we also announced that we will retail that for starting at 50 million euros. And the response to that was, a lot of people said, that's a really large amount of money, but you need to look at that on a cost curve, per qubit basis. And actually, this is a 10x reduction in price from, on a per qubit basis from where we are today. So actually, if you look at it that way, anyone claiming that they'll do it for less is just, not telling something realistic. Like, a 10x reduction in two years' time is hyper aggressive, and it goes for the other parts of the stack as well, right? Like, take high density ribbon cables, these cables that you need, and you need quite a lot of them. to get to the large scale quantum compute.
Sounds like tens of thousands, actually.
Yeah, well, in VIO 40K, you'll need 40K of those, right? To power, say, a typical tunable qubit with tunable coupler design will take about 4 signal lines per qubit on average. So therefore, for 10,000 qubits, you need 40,000 lines. Well, today, these are about €1,500 a line. And so that needs to come down pretty aggressively. But if you look at it from a first principles basis, what's okay? Well, it's a thin layer of some kind of plastic material with a thin layer of superconducting metal and then a thin layer of plastic. That's it. And so on a material basis, that material floor is a cent. Maybe let's call it 10 cents. Let's give some room for margin. So the difference between 1,500 and 10 cents, that's all volumes and yields. And so this whole, I think this industry is going through a transition where, this whole framework around, it's not science, it's engineering anymore. Well, actually it's much more transitioning now to economic cost curves and bringing up those volumes because, technically you can make a lot of those cables. It just needs to be much cheaper.
Right. And so you just said sort of it's not science, it's engineering now. Your VIO architecture, you see a clear path to getting to tens of thousands of qubits with that architecture.
Yes.
That's incredible. That's really cool.
Sorry.
You'll walk me through, we've mentioned VIO a few times. Like, what exactly in broad strokes, what is VIO?
So VIO is a 3D QPU architecture. And what I mean with that is it's a way to make a very large quantum processor or an array of qubits out of many smaller modules. And a VIO module, what that typically looks like, it's a qubit plane consisting out of a few qubit chiplets. So a big chip out of many smaller chiplets that resides in an array of vertically placed chips. And so that is basically a cube of silicon. And that is really important for a variety of reasons, but one of them is it gives you real estate to integrate other parts of the quantum computer in this stack of chips, which, if you get to really large qubit counts, actually becomes a very important thing to resolve, because otherwise you just simply run out of space. It also gives you a way, because it is modular, to actually make these things because of yields. If you want to make let's say you want to make a chip with 1 million qubits, well, that is just technically infeasible. But you can make, a chip of, say, maybe 100 qubits, and you can attach those together. And then third, going from science to engineering to like industrial scale up, because it is silicon based, it is producible at a massive scale because, we just use normal semiconductor tooling and processes.
So
and that combination is really important.
Are the chiplets individually fabbed and then combined into a chip, and then the chips are combined into these layers, or is the chip the sort of the unit that you're fabbing and then combining the chips into the layers? I guess I'm just asking: is a chiplet is a chiplet a standalone unit with a certain number of qubits that then gets connected to other chiplets?
Typically, yes, and you'd want that to be that way because it makes it mass producible. It's just this repeatable unit cell that you can produce at a very large scale, and therefore cost collapse. And I think what's really important to emphasize is that. So right now, the field's stuck at 100 qubit chips, the size of an A4 piece of paper, and so you can't really, get to scales of, say, 10,000 qubits and beyond, which we will need to do something, actually economically relevant, without resorting to things like networking. Whereas if you do, and this is already proven in experiments in real life, a connection on qubits between two chiplets is as good as a connection between two qubits on a single chiplet. So intra-chip fidelity is as good as inter-chip fidelity, which means that you can scale up without losing compute power, and therefore it is exponentially better than a network-based alternative.
So these are superconducting leads that bridge from one chiplet to another and one chip to another. They're all interconnected with superconducting leads, just as the qubits themselves are on the chiplet.
Exactly. It is just, from the perspective of the user, it is just one very large chip.
Yeah, you said a cube. I'm sort of imagining this cube of qubits floating in the bottom of a Delft fridge with 40,000 leads coming off.
Maybe we should clarify that a little. It's little cubes that we then attach together. So the eventual thing is more of a square, if you will.
Okay. That's amazing. So each of those units that you're connecting together, how many qubits is sort of in a chip that's made up of chiplets?
That's a design choice to some extent. And what that will typically also depend on is what are the yields of your qubit chiplets and what are the yields of attaching those together, right? There'll just be some optimum there.
Yeah. Again, back to the economics, as you said. It's it's the yield economics. That's really interesting. So we mentioned sort of the packaged QPU business. You have two other sort of models for engaging with the industry. One is more of a foundry services, right? So you're actually collaborating with vendors who are seeking to build a full quantum computing system, and you're providing the chip foundry capability, much in the same manner as TSMC provides chips to Apple and NVIDIA and others, right? Is that a good analogy?
I think so, yeah.
That's really cool.
I think one way to think about our QPU business is that is, our internal design teams designing QPUs optimized for quantum error correction on our own platform. But we can also take in, indeed, customer designs on our own platform. And we can even take in qubit chiplets of customers on the VIO platform. So it's really these three verticals in which we operate.
Interesting. So they think they have, the magic qubit design, you can actually integrate that into the chiplet, or if they want to leverage your qubits, but have a different sort of, base system architecture, you can adapt VIO to that in the way that you connect the individual chips. That's really, really interesting. So you're working with Seek already on sort of a this type of collaborative model, right?
So we have a bunch of customers, and Seek has been a wonderful customer and partner basically from our early days. And we, I think the work that they're doing on SFQ has the potential to be really important.
That's very cool. And then, I mean, when you describe that sort of range of services, that's, I guess, the lightest services that you provide is just packaging, right? Like somebody brings you their full QPU, their just the silicon or the chip itself, and then you package that up into something you can integrate into a full system design. That's another sort of aspect?
Yeah, so we're really positioning ourselves to get the entire industry to scale using VIO, because this is the bottleneck that is keeping back the quantum industry. And so, we believe it to be, for quantum computers to make, the positive impact on the world that they can make, they need to be larger and they need to be so in an economical way. And that last bit, a lot of, people in the industry typically tend to forget. But getting there in an economic way means making it at industrial scale, at high volumes, with very high, utilization rates and efficiencies. And so therefore we position in a way that we can get, everyone to scale using VIO. And there's, of course, there's some flywheel effect in there, right? Like the more customers we get on our platform, the better the product is that we can provide to our customers.
Right. So, I mean, this is essentially an open systems approach to quantum processors. How difficult is that to sort of try to establish or champion an open standard or open systems architecture at this super early stage of a technology?
So it's been surprisingly easy. So we call this the quantum open architecture. Indeed, it's been surprisingly easy because it just massively lowers cost and development times. To start building these systems and then actually to do interesting stuff. Right? Imagine. Again, I think the analogies to the semicon world are really like interesting to look at. Imagine if you were a company today, even if you were a large company today, and you wanted to, I don't know, do interesting stuff in AI, but you first had to develop a 3 nanometer process to kind of make the chips, then design them and write the driver. Right? It would be completely ridiculous. And in quantum, the reason that everyone was vertically integrated is that that was the state of the industry. But as you get to larger scales, it becomes completely ridiculous that everyone is doing that themselves. That will just be too inefficient.
It's interesting. From that perspective, you could say that every disruptive technology is actually an incremental, progress, right? Because you're building on every prior sort of incremental increase in like the smaller and smaller leads in lithography for semiconductors, for example. That's a many decade effort that got to a GPU or a modern ARM chip or whatever. Yeah.
Yeah, and I think indeed, like it's compounding improvements that if you lower cost every year by 30%, yeah, then at some point it becomes completely unbeatable. And if you get, it's the same again with chip making. Whether you make 10 or 100 chips, your marginal cost barely change. It's all about depreciation, right? And so if you sell commercially 100 chips, your competitor sells 10, well, your margins are roughly 10 times better. But that's a flywheel, right? Because if that means that you can get many more. You can just make a much better product and reinvest much more in R&D, and that's over time that difference gets so big that you can dominate a space.
Yeah. I suppose that really kicks in once the chips that we're producing, that we're shipping in quantum computing actually have some commercial application, right? I mean, then you've got a product that there'll be some demand in the market for repeated, like, the customers will multiply, as opposed to today where it's, there's a small number of customers that tend to be really at the moment concentrated in the public sector, or at least public-private sector, where ecosystems are trying to be, NQCC or IQCC, as I mentioned before, those types of efforts to build quantum industry ecosystems. But at some point, there'll be quantum data centers and quantum applications that the enterprise in some industry or other will actually want to access and pay money for, and then your economies really kick into overdrive.
Yeah, and I think what's really helped with that view is the current hyperscale data center build outs, right? Like, not getting into the whole discussion whether that's whether we're overbuilding there or not, but that's like north of $7 trillion cumulative capex investment by 2030. And if you look at it, in that way, like, the thing that restricts that is access to electricity. But so quantum computers, hyperscaled quantum computers. So we're talking maybe quantum computers of $1 billion plus, like very large pieces of compute and infrastructure. In that context, not only is $1 billion, reasonable, but more importantly, quantum computers will provide exponentially more compute in certain use cases per dollar or per watt. Let's interchange these, and that means that even if that percentage is small, I would argue that percentage is going to be quite large. But the honest answer is we don't exactly know, right? Going back to that would be equivalent to a universal theory of everything in physics, if you could answer that exactly beforehand. But even if it's a couple percent, that is a massive market. And yeah.
Yeah, you mentioned access to power being the bottleneck, but there's another bottleneck, which is access to capital. As a European company, I've heard other European founders say that in quantum, it can be difficult to access the scale of capital, especially in hardware, from the European private markets compared to the American markets. Is that something that sort of added friction to the growth of QuantWare?
I mean, obviously, capital markets in Europe and also in the Netherlands are not as developed as in the US. I don't think that's a controversial statement. Something I am very active in advocating for, and trying to help develop, especially here in the Netherlands and Europe. However, it also, of course, depends a little bit on the rate of progress and the momentum you have as a company, right? Good companies will get funded, and yeah. So I think for us, I think it would be better if the European ecosystem would develop further. I think there's a lot to be gained by that. Um, we have, in general, not been restricted by access to capital ourselves, though.
Okay, good. Yeah, I mean, you mentioned, I mean, there's a lot to gain. I mean, in a way, I think that there's something like 30 countries that have national quantum strategies around the world now with, last I looked on the Curaca site, it was something like 70 billion. I'm sure it's more than that now, committed publicly. Who knows what the actual sort of plans scale up to, but I feel like the Dutch ecosystem is one of the examples of how to do it. I mean, you came out of, as you said, QuTech, which is part of Delft, which is the D in quantum delta, and you've got QDNL participations on your capital, on your as an investor. It feels like the skill base you're able to recruit out of at QuTech really is kind of a dream team of talent. When you look at the experience of your sort of founding team and the people who've been able to recruit, what do you think that sort of the Dutch sort of punching above its class, for lack of a better term, it's like the impact of the Dutch ecosystem seems outsized compared to the size of the country. What do you think that sort of is attributable to?
So first of all, I think you're right, and I'm not saying that because I'm a Dutch and standing here in that ecosystem. I think you're right. I think the reason for that is consistent long-term investment and policy, and QuTech I think is a prime example of that, right? Like that is well over a decade of governmental investment at a serious size, and also attracting serious international companies to do their research here, right? Microsoft, Intel, etc., etc. And then following that up with more than 600 million to Quantum Delta and NL, which of course for the Netherlands but for any country is a sizable amount of money. And I think the key thing now is, I think really this is kind of a make or break moment. We now have this very diverse ecosystem with all kinds of parts of the ecosystem, parts of the value chain, especially centered here around Delft. And we have this real opportunity to become this, value chain, concentration point, which has very economical benefits, but also deeply national strategic benefits. And the key thing for that, you mentioned it already, is access to a large scale of capital, right? Like in the end, this is not these companies will need hundreds of millions of capital. That's just the nature of this business. The market is very much big enough to support that. But that needs to be, there in time, and it needs to be accompanied by the right, governmental policies around it. And of course, we're now getting to a size where we'll be in different countries as well. Like we will internationalize. But I think what was a really positive sign is a few weeks ago, there was the Wenning report was published. This is a report written by the former CEO of ASML, comparable to the Draghi report for Europe, if you're familiar with that, where one of the recommendations was to invest 9.4 billion euros in quantum in the Netherlands. And I think really that is the scale we need to be thinking of.
That's incredible. Are you lining up already for that?
I mean, obviously, this is a report that will then go,
Yes,
to the government and to politics, and so I don't expect there'll be 9.4 billion on our bank account tomorrow. But I do think it's a very positive sign, that the kind of momentum and the long-term policy support that quantum
Right.
has here in the Netherlands and in Europe.
Yeah, that's fantastic. So, okay, so this is all super exciting. Can you leave us with any sort of prediction forecast? Where are you going to be with QuantWare with VIO in a year or two in terms of your roadmap?
So in 2028, the first VIO 40K arrays will be shipping to customers.
So that's 10,000 qubits.
That is up to 10,000 qubits. And so 100 times more and 100 times denser than anyone else. We're really looking forward to see the impact that will make.
That's incredible. Okay, well, you're going to have to come back when you ship that because I want to talk about it. That's great, Matthijs. Thank you so much for your time. This is really exciting. I've been a longtime admirer of QuantWare, so it's great to have a chance to dig into it with you.
Pleasure to be here. Thanks for having me.
I want to thank my guest, Matt from QuantWare. Once again, I really enjoyed that conversation. This episode, again, brought to you by qubitsok.com, the signal in the noise for your quantum job search. Learn more at qubitsok.com. If you want to go deeper on the topics we cover, research highlights, commentary, and the occasional behind-the-scenes look at what's coming up for the show, sign up for the newsletter at newquantumera.com. It's free, and it's the best way to stay in the loop. And if you have an idea for a guest, a topic you'd like us to dig into, or just want to say hello, reach out through the website. I read everything. If you're enjoying the show, please subscribe wherever you listen to podcasts and leave a rating or review. It genuinely helps new listeners find us. And if you know someone who's quantum curious, send them an episode. Word of mouth is still how most people discover the podcast. Thanks for listening. I'm Sebastian Hassinger, and this has been The New Quantum Era. Theme music by OCH. See you next time.